It's my pleasure to introduce Dr. Yuhang Nan. He's a postdoc research associate here at Purdue University. He earned his PhD in the School of Computer Science from Fudan University in China, with his honor being the 2018 ACM SIGSAC China Doctoral Dissertation Award. His research interests span privacy leakage detection in mobile and IoT platforms, security enhancement for IoT systems, as well as cyber attack investigation with audit logs. So with that, I'll turn it over to Dr. Nan.
Thank you, Jerry. Okay, good afternoon, everyone. It's good to be here. So today I'm going to talk about a new approach for identifying and analyzing private data in mobile applications, which can be used for detecting privacy leakage. So in this talk, I will start from showing a motivating example. It shows a new type of privacy leakage pattern in mobile apps. And then I will introduce the ClueFinder framework, which is used for identifying new types of private data from the mobile app code. With this framework, I will show a large-scale measurement which enable us to better understand the scale and the risks of private data exposure in the app market level. And I will also show a set of interesting case studies about how and why such privacy leakage happened. And lastly, I will discuss some future work following this line of research and conclude this talk. Okay, as we know that today's mobile applications, they are more composed than written, meaning that there are many third-party libraries integrated to the apps. It is very common that an app may integrate some ad libraries, like a Mobi, Apps Flyer, etc. for monetization. Also, the app could integrate a variety of social network SDKs. These SDKs are supporting the app for the single sign-on function and allow the user to share their in-app content to their social networks. Further, the developers may also likely to integrate analytics libraries, which collect different types of data for bug fixing and user experience improvement. However, such functionalities comes with significant privacy implications to users. As previous studies show, since these apps are hosted in the same container with the developer's code, technically, they can freely collect and share any kind of sensitive data without user consent. Further, they are also capable to associate users' different activities together and infer users' other secrets, because most of the SDKs, they are very popular and they are big player in the market. They can distribute it in the multiple apps of the same device, so they can use the unique user ID to associate different users' attributes. Let's take in the following case we have discovered as an example to see how such privacy leakage happens in a very stealthy way. So here, a third-party library is integrated by a popular news app for social network sharing to different popular platforms like the Facebook, Twitter, and WeChat. We call this SDK as a social network sharing syndicator. All such behaviors looks pretty normal, and also it's actually very helpful to developers, because with this SDK, the developers don't necessarily to configure each social network platforms in their apps one by one. However, when the user shares the in-app content to her social network, likely she will not know that this process is actually handled by this third-party library instead of the app itself. And she will also not know, in order to do this, the app needs to handle the user's login credential, which is an access token to the third-party library for completing this functionality. Okay? So even worse, since the access token allows the access to user's social network account with several critical information, we are surprisingly found that using this token, the library is actually also collecting all available sensitive data with the shared content to its own server, with the very detailed user demographics, including the user's location, gender, education, etc. The motivation behind this is quite simple. From the perspective of a third party, every piece of data is very helpful for more precisely targeting the audience when they do advertising. So that's the reason why they collect it, and they are going to sell it, share it with the advertising networks. To find against such stealthy behaviors, so the preliminary question here is how can we automatically identify such sensitive data in a generic way? Then we can further integrate different kinds of existing analysis techniques to further tracking this data. So when we are talking about the automated privacy leakage analysis, previously, traditional sensitive sources in mobile apps are usually labeled by a set of fixed APIs that are referred to the system-controlled private data. These will include the location, contact information, SMS, and phone number. And later, to expand the scope for detecting privacy leakage in a more fine-grained manner, researchers also bring solutions to identify the user input data. Basically, they parse the layout resources of the mobile applications and identify what kind of input are sensitive. However, the more complicated case here is user-sensitive data from the app's server side, especially after the user logs into her account and download the data from the server. In this case, either the system API-based or the UI-based app labeling approaches are unable to effectively locate such data because regardless of their sensitiveness, loading such information always goes through those generic system API without specific characters. One may also consider why we don't capturing such data by intercepting the network interface with runtime analysis. Yeah, this works in some cases, but it is limited in both coverage and scalability. The coverage could be limited because modern apps always require the complex logging conditions to trigger the real network traffic, which contain those sensitive information. And also, automatically exploring and testing in runtime is very time-consuming, which is also not feasible for a large scale and vetting when we want to detect those privacy leakage. So to overcome such limitations, a key observation in our approach is that most apps today, they contain a large amount of semantic information in their code for supporting software development and maintenance. For example, the program elements like the method names and variables, they are all given meaningful names with the plain text to explain their related content, such as the value of a certain key. So this actually provides us the opportunity to discover the sensitive data from mobile apps rather than analyzing the real network traffic. So based on this observation, we first developed ClueFinder, a novel technique that mines the decompiled app code to recover semantic clues for identifying sensitive information. The design of ClueFinder, covering not only those sensitive data labeled by system APIs and user interfaces, but also cover the server-side private data. Then, armed with more sensitive data sources discovered by ClueFinder, we are able to evaluate the exposure risk of such sensitive data over 400K apps. The results enable us to gain new insights about how private data is accessed by different third-party libraries at a large scale. Okay, so although the app code is semantics rich, recovering those truly sensitive data sources from the code is by no means trivial. So the first challenge here is how to effectively solve the various ambiguity of the text strings in app code. As shown here, in many cases, the presence of a sensitive keyword may not represent any sensitive content. And secondly, program elements that carry sensitive tokens may not carry sensitive content by themselves. Such examples could be a log information with error message or an API for setting string labels to its user interfaces. Both of these actually do not carry sensitive content even when these code are executed at runtime. So here we present how ClueFinder tackles these challenges step by step. So the idea behind ClueFinder is to first quickly screen across the app code to locate those privacy-related tokens with program elements, and then semantically evaluate those program elements to drop false positives. It mainly includes 4 components, which are the semantics locator, semantics checker, structure analyzer, and the leakage tracker. So for a given Android app, the semantics locator first disassembles its code from the APK file and identifies the program elements that carry those sensitive tokens. These sensitive elements are then inspected by the semantics checker. The checker uses NLP techniques to determine whether the identified tokens are indeed the main subject of each element. And these program elements, those meeting the requirements of semantics checker, will further go through a program structure analysis. The structure analyzer classifies each function invocation as either sensitive or not. Lastly, those reported sensitive elements are delivered to the leakage tracker, which traces the propagation of those sensitive information. So now we come to the detailed explanation of each module. To identify privacy-related data through the semantics of program elements, we first gather a set of privacy-related keywords as the knowledge corpus. So these keywords are gathered from multiple sources, including Google's privacy policy and reports from the Financial Times and related research. Then, the semantics locator takes all possible elements from the decompiled resource in focus, including the method names, variable names, the constant strings in parameters for each statement, if there are any. For all these texts, ClueFinder uses a set of pre-processing steps to capture as much as possible those privacy-related semantics. So we use the word splitting to split those delimiter and capitalized letters, and we also use stemming to extract those word prefix to avoid missing variations of the related text. So the goal of semantics checker here is to perform a grammatical analysis over such privacy-related tokens and filter out the match terms that are not serving as the theme of the semantic context. Specifically, we first use part of speech tagging to determine whether a privacy-related keyword is actually a noun in the term of the sentence. For example, the address in the term address this problem here is a verb. It just describes the action happening to another word, so it is not likely to represent a physical home address. And also, we use the typed dependency parsing to check if the privacy-related keywords shares a specific relation with other words. So the typed dependency parsing provides a simple description of the grammatical relationships in the sentence by providing a more structured format to analyze those sentences. Consider the following example. In this method name, the location only holds a compound relation with update and time. So where the main subject of this term is to get time interval, which is indicated by the direct object relation between the term get and interval. So this method does not indicate any existence of location data. Taking another example, the keyword phone here only holds a possession nominal modifier relation with the term my. So the direct object relation here is between design and T. So this short term indicates that the phone is not actually describing someone's phone number here. Okay, so after the above analysis, even when a sensitive token plays a central role in the name of a variable or a method name, such program elements may not necessarily related to private content. For example, the first statement in the red only returns a Boolean value indicating the existence of a specific key, and the last statement here only reports a message indicating the location information have been updated. On the contrary, both the second and the third statement indicate the existence of the sensitive data because of their return value and their parameter values, respectively. So here we use the structure analyzer with an SVM-based classifier to filter out those irrelevant statements. The structure analyzer here employs a set of program structure features to determine whether a given program statement indeed contains data objects. In detail, we chose the following features, including the method name, the class type of the parameters, return values, and base values, as well as the constant variable patterns. Our key observation is that when these labeled elements are involved in data read or write operations, and almost always these operations are related to sensitive information. Such evidence could be as simple as the presence of the specific keys from the method name, like get, put, set, something like that. And it also could show from the patterns of different appearance of the parameters. Like if the two parameters in the method invocation is constant and variable, very likely the constant string is actually describing the actual values in that variable. Yeah. Okay, so after this, in the Leakage Tracker, those statements together with the privacy-related semantics will be treated as the actual sensitive sources for detecting the information leakage. After we labeling those either parameters or the return value, we can use existing data flow-based Tenta analysis to track those sensitive data. And what is unique for ClueFinder is its utilization of semantics can enhance the Tenta analysis, which brings a more efficient way to detect the privacy leakage. Looking at this example, so traditionally if we want to track a location data from a mobile app, we will go first from the system API, which is shown in line 1, and extract this data as sources. And then the data will flow through several steps to line 7 and line 8, and finally leaked out. However, with ClueFinder, we can directly confirm in line 7 and label it as a location data because there are semantics in line 7. With this, actually, it helps us to reduce the data propagation paths, reduce the length of this path. This will ensure a more efficient and more accurate data flow tracking. So we implemented ClueFinder with a mix of Java and Python scripts. the Java side is responsible for decompiling the mobile app code, and we also use the Stanford parser in Java to implement the NLP analysis part. And also we use the scikit-learn in Python to implement the SVM classifier. So to evaluate the effectiveness of ClueFinder, we performed a manual validation steps. So we randomly chose 100 top popular apps from Google Play and ran ClueFinder. After the output, we go through each identified statement and data to see if ClueFinder correctly labels it. And we found that it has around less than 10% false positive, which gives us a final precision of around 91%. And for the false positive and false negative, some of the false positive are caused by insufficient semantic analysis. In this example, ClueFinder reports that the variable R1 here contains the access token information. However, as we can see here, since the access token is actually, access token is not in here because from the semantic text, it said the access token is saved to some extra place. That means we will need to bring more detailed NLP analysis to tackle these false positives. Also, ClueFinder have some kind of false negatives. In this example, ClueFinder missed this gender information because usually the gender is represented by a string. However, here, the developer used the integer value to represent the gender, so ClueFinder missed it. So this case can be addressed by including more training data or add some heuristic for the specific type of information. So here we will talk some about the limitations of this approach. Since the ClueFinder is a semantics-based approach, it is limited to those deeply obfuscated code if all the semantics information were removed from the decompiled app code. However, this does not mean ClueFinder cannot tolerate any obfuscation, because even with moderate code obfuscation, the semantics information is usually preserved in some critical locations. For example, the system-level code structure features like parameter types and return values cannot be obfuscated, and they can still leverage by ClueFinder as features to determine the presence of the sensitive data. And besides, due to some practical constraints in those code obfuscation, those methods related with reflections and the interfaces of third-party libraries, they usually will not be obfuscated because they need to make sure developers can easily integrate those APIs to their app code. Actually, we only found that there are around 11% statements were obfuscated during the cross-library invocation, meaning that most privacy leakage can be detected by ClueFinder. So now we come to the large-scale measurement study over 400,000 apps. In our study, we crawled apps from either the official Google Play market and a top popular third-party app market in China. Note that in this study, instead of detecting privacy leaks to the network, we only looked those leaks of sensitive data to third-party libraries from the app. This is because once we identify an untrusted library obtain this private data, it often can manage to send out the data through any kind of covert communication channels. So among all the apps in our data set, ClueFinder totally discovered around 26% of apps leaking leaking users' private data to around over 3,000 third-party libraries. And note that in here, we only focus on the findings related to the source, those missed by prior approach, meaning that we already exclude those typical private data like IMEI, ICC-ID. Yeah. And among the popular Google Play dataset, we found nearly 40% of the apps are leaking out user data. And our further analysis showed that almost half of the identified method invocations, they are related to HTTP and HTTPS, meaning that they are indeed leaked out. So this actually serves as a lower bound to measure if they are really leaked out to the network. And our evaluation also found averagely each app could expose 8 unique sensitive data items to about 2 third-party libraries. And also, if we compare these two data shown in the red square, we can see that unofficial app market tend to integrate more libraries involved in private data leakage. Likely because these unofficial market mostly has less restrictive vetting process, and they are more tolerant to those suspicious behaviors. Okay, so from the ways this library interact with their hosting apps, we summarize their leakage patterns in the following different types. First, as shown in our motivating example, some third-party libraries are deliberately harvesting information from apps. This sensitive data could be leaked out without developers' attention, not to mention the user's awareness. And interestingly, we also found that developers will send the private information by apps, but by the interface of those third-party libraries. And there are two subcases. The first one is the developers intended to disclose the sensitive data of users. And the second is developers unintended overshare the private data of users. So as shown in this example, it's an intended disclosure case. Here is a popular dating app, and it integrates a third-party library which is called AppBoy. So every time the user seeks for a nearby potential dating target, this app will send users precise location, bio information, dating targets, name on Instagram, such information to the third-party library. However, at the meantime, we did observe these data are also shared to the app's own server. So basically, these sensitive data are shared with multiple copies to different parties. Yeah. And this case is a unintended oversharing case. So this app is called SnapT, which is used for customizing tea design and shopping. So we found that it is sharing the user's information to a third-party library. The library claimed that it can help to understand who your users are, see what they do before or after they sign up. Okay, so obviously it is collecting private data. However, we also observed that the user's access token, which is used for sharing information to the social network, is also sent out to this third-party library. This information is actually not necessary to this third-party library. However, the developers just because all this data is encapsulated into a JSON object, so the developer just directly invoke the API and send the whole data package to the third-party library. Okay, so in terms of the leaked content, we also see there are new strategy to obtain the user's location-sensitive data. because with the more and more restriction of accessing GPS location information by the system, the apps tend to first save the location data in a normal or benign usage scenario. And later, if the app or third-party library needs this location data, it will just send the previously saved information to the server to avoid frequently invoking those sensitive system APIs, and hence can avoid the user's awareness. And also we observed that there are many third-party libraries are aggressively collecting the list of installed applications from the user's device. And as shown by one of the third party, it claimed that the user targeting allows you to target users that have or don't have specific applications. Okay, so we know they are basically persistently monitoring users' apps installation and for the advertising. So let me talk about some of the future works. So the ClueFinder enables a non-trivial way to identify different types of private data. And it can better support the privacy leakage detection because it enables a better coverage and scalability when we do privacy leakage detection. Also, with the tools like ClueFinder, we can give user better awareness about the privacy leakage. For example, we can generate the privacy labels by analyzing those apps and show these labels to the user before the app installation. And also, we can identify who is to blame about those privacy leakage. Is it the first party or the third party? And last thing is ClueFinder can better support those privacy compliance analysis. As we know that like regulations like GDPR, they are really pushing hard to protect users' private data. So using things like ClueFinder, we can first analyze what the app code is actually accessing, and then we can compare with their privacy policy to differentiate, if there are anything they missed, they didn't disclose to the user. Okay. So to conclude my talk, we first proposed a novel technique for identifying user-sensitive data. And this helps to extend the scope for labeling more sensitive data from the app code. And also, we conducted a large-scale measurement about privacy exposure risks to third-party libraries. And we gave a set of findings to highlight the importance of data protection in today's software. Yeah, that's it. Thank you. So I'm happy to answer if you have any questions.
No questions?
No questions?
Okay.
Good.
Okay, so thank you very much.
Thanks.
Appreciate it.
Yeah, thank you.